anybody who was not here last time? Here, hold on, there's more. One of those. Take one of those. Take one of these. Let's see. Am I missing one? I think that's it. All right. First, we'll start with any questions you might have over homework or the take-home. Anybody? Not all at one time, please. Raise your hand. No? Everyone's doing great? Okay. Then you should have asked me for help on part B, number one. But yeah, everything is partial credit, so you will get something for doing some of it. Yeah. Yes. 10.2, number 29. Did I assign 29? Did I? Did anybody write down the homework I sent in the email? I don't believe it was 26. So I won't cover 20. If you want to talk about 29, you can come down to my office and we can do that. So do you mean 26 then, or just forget it? Okay. All right. Anything else? I will say that with the number 26 and with number 20 or number, what is it, on the take home, it's the one with the plane. Is that the first problem? Right? We talked last class about vectors, right? And we said that you can orient a vector in two-dimensional space. You can orient it, to the origin. You can slide it around, right? And then you could then talk about the angle here, theta. And if you're given, let's say, the speed of something, the speed would be the length of the vector. All right, so let's say the speed of this is s. Then s is how long that vector is. Remember, a vector written in its component form has two pieces to it, right? It has, let's say we call this vector v. It has two components, v1, v2. Then s is the length of the vector v, right? So when we're talking about speeds of things, it is a vector, but it's not given to you directly. What I've given you is the angle of the vector, and I've given you the length of the vector. What you need to do is somehow reconstruct its components, and that's just trigonometry. It's just the trigonometry of a triangle. So just try and recover that, okay? Nothing else? I was thinking about it, and I haven't done this before, but I think I'll do it this semester. I will give you bonus points for turning in the take-home early. I'm not going to say how many points, but if you get it to me early, I will consider bonus. I will give you bonus. I just don't know how much yet, right? And it's kind of twofold. It'll keep you on track. It'll motivate you a little bit. And for me, grading these things is very time-consuming. All right, think about 30, 28 of you, and this is a pretty short take-home. This one right here, what is it, 4 or 5 questions, right? And the answers, the work isn't very long, but they get very, very tedious. In fact, I have, these are the answers. These are the worked out solutions for all your take-home exams. How much is what? To buy it? And so it's a lot of work, and I would like to get some of them early so I can knock them out, you know. So all you have to do, it has to be done. If you're going to turn it in early, it can't be scanned and emailed. It has to be physically handed to me. All right, so drop it in my office, my mailbox, or something like that. But please let me know you're doing it, okay? So if you go by there and I'm not in my office, leave it with the attendant. Make sure you get some sort of verification that you dropped it. Maybe make yourself a copy. I've had them dropped with me before, and they've been lost before. So always make sure you have another copy of your test just in case. All right, and then let me know by email. Hey, I left it in your mailbox. Blah blah blah, and then I'll give you credit. Okay. All right, we are going to move into. We finished 10.3, right? So we're going to move into 10.4. Remember my keyboard was doing that weird thing last class? I still haven't figured it out. So I have an extra one, so I just brought it instead. But very strange, like the keys are doing things they're not supposed to be doing. All right, 10.4. So we said last class that when you have two vectors, that we can define an operation between them called the dot product, which is a way to kind of multiply them together. But we said that there were two different types of multiplication of vectors: dot product, cross product. So we did the dot product. Now we talk about cross product. I thought about just a one-question quiz today, and it would have been the dot product of two vectors gives you what? A number, a scalar. Okay, that would have just a general, just a very easy quiz. But remember that, okay? Dot product gives you a number. Cross product will not be that, okay, as we're going to see. Before we proceed, though, let's just make sure we understand that with vectors in 2D or 3D, that you can rewrite them using these, what are those? The I and the J, those unit vectors, right? The standard basis vectors, I hat, J hat, and then in 3D, K hat. So if you look at the components of the vector, and you just throw the first component in front of I, add to that the second component in front of J, then that's the same vector. All right. We know the dot product. Second type is the cross product. The only thing that well, it's a big thing. It's not the only thing. We have to pay attention to the fact that when we deal with cross products, the cross product is only defined in three-dimensional space. So in 2D, there is no cross product. In 2D, there is a dot product. In 3D, there is a dot product, but cross product only exists in 3D. Yes. You can. You can define dot product in any dimension. Cross product, there's other names for it, though, once you go higher. Yeah, I didn't really talk about that. We're going to deal solely with vectors in R2 and R3, but you can have vectors in Rn, and there's actually something called R infinity, which is infinite dimensional space. You can have a vector defined in that also. All right, so we've got the idea that we have to be in 3D in order to use cross product. There will be a way later that if we have something in 2D and we want to cross something, two vectors in 2D, we can extend 2D into 3D, and then we can cross. But for now, we're just going to say we're sticking with 3D. All right, so here's the cross product. Let's let U and V be two vectors, and then the cross product is denoted with this. It's like the old school multiplication symbol, okay? It's a cross. And it can be computed directly with these these two formulas right here. Now you can memorize these formulas if you like. Okay, if your brain works that way where it's easy for you to memorize formulas, memorize it, fine. Okay, or you can do it using a process, and that's the way most people learn to do cross products. All right, so that's what I'm going to try and do in this class. So there's all these different ways of doing cross products. I'm going to show you two different ways. All right. The first way is by using this little table. All right. And I'll show you how to use this table to get the cross product. And I also expect you to be able to do a cross product on your calculator. So most of you have calculators that have built into it the cross product. If you do not have cross product on your calculator, if you do not know if you have cross product, then you should get with me. I know some people use TI, 83 or something, and it doesn't have the cross product, but you can program the TI-83 to do cross product. So whoever does not have cross product on their calculator should come down to my office. We'll get you all there, at one time. I'll take you through how to program it, and then you'll have it built in. But the thing is, you don't want to be doing cross products on a test. The in-class test, you don't want to be doing cross products by hand. All right, it'll take too long. Waste your time. But we do need to know how to do it manually. So here we go. So we're going to do the cross product of these two vectors. So I'm taking the vector u, 2, -3, 5. The vector v is 4, -1, 3. I noticed that a few students, at least YouTube tells me that people watch a video or not. I did notice that maybe a few of you watched the video from last class. Did any of you have problems getting the video to run or anything, or to load? No? Okay. All right, so here's using this table. The way that you can do it is you write I'm just going to write I instead of I hat, ijk, ijk. We're making a table. Okay, and then below it, you write the two vectors. If you look on, I have this formula on page, or on 10.4.4, you write the u vectors components out underneath the ijk, and then you do it again. So I'm going to write u, the components are 2, -3, 5, and then 2, -3, 5 again. And then you write the v under it, 4, -1, 3, 4, -1, 3. Has anyone that's done cross products seen this table before? Yes, some have, some haven't. That's why I show you two different ways. Okay, so now what we do is we start with the I, and what we do is we move diagonally across and we multiply. Okay, so what's I times -3 times 3? That would give us what? -9i. Okay. And then we do the same thing for j, moving diagonally. So j, 5 and 4 multiply to be 20j, right? And then we do the same thing with k. And that gives us what? -2k? Like that. Now what we're going to do is we're going to do the next I, which is here, and we're going to go diagonally the other direction. So the colors are getting kind of mixed up here, so I'm just going to say we're going to go across diagonally here, here, and spit that answer out here. So I get what? -5i. And then I do the same thing with j, 6j. And then the same thing with k diagonally, and we get what? -12k. Okay. All right. Now here's the major thing you have to remember. What we're going to do is we're going to combine all those together. We're just going to add them together, like how many I's, how many J's, how many K's. But everything we did diagonally to the left, we have to change the sign. So it's really going to be 5I minus 6J plus 12K. Then everything else that we did diagonally to the right stays the same. Minus 9I plus 20J minus 2K. And then put them all together. How many I's do I have? Negative 4I. J's 14, right? And then K's 10. But that's the same as the vector negative 4, 14, 10. Well, I think I said last class, I prefer this way. I use that way almost exclusively in the class. I don't care. It wouldn't be wrong. I wouldn't count it wrong this way. Well, let me show you this other way, and then maybe that is the way you did it. Okay, so that's the first method, all right? I think that's a long method. Okay, it's longer than the one I'm going to show you now, but at least it's a method, all right? The next approach requires that you understand how to take the determinant of a matrix. So that's why sometimes this is a method that people are like, what? Determine what? So if you have a matrix, A, B, C, D, that's a 2 by 2 matrix, then the determinant of this 2 by 2 matrix is what? A times D minus C times D. Or sorry, A, B, C, D, B times C. So what you're doing here is for a 2 by 2 matrix, you're doing A times D, so you're going and you're multiplying across that way, right? And then you're subtracting from that going the other way, B times C. Do y'all see that? How many of you have done that before? Determinant. Okay. No questions? All right, so we need that in order to do a cross product, the second method. So here's the second method. Let me take those same two vectors. I'm going to write out the components, and then underneath it, 4, negative 1, 3. And then above it, I'm going to put I, J, K. How many of you have seen this? This look more, okay. This is a much faster way of doing it, all right? So the first thing we're going to do is we're going to try and determine what our I's are, okay? And to do the I's, what we do is if you're with your page, okay, writing it, you put your finger over the I column, and you do the determinant on this 2 by 2 matrix. Okay, so cover that up and do this determinant. So what's the determinant here? Negative 9. So I'll cover it up here like this. This will be easy for me to do. So I'm covering this up, right? And I'm going this, which is what? Negative 9. Negative 9. And then I'm going to go minus here. Negative 5, which is negative 4. Correct? And that is what goes in front of this. Now, does that match what we had before? Yes? Okay. So that's how I get the I. With me? How do we get the J? You cover up the J, right? So now I'm going to come in here and cover up J. And I have a 2 by 2 matrix here. Here's 2 of them, right? 2 and 2. And I do the determinant there, but there's one little catch. What is it? You have to change the sign of whatever you get. So I'm going to do 2 times 3, which is 6, take away 20, which is negative 14, but then I need to change the sign. You change the sign on the J. Okay, that's the only one you change sign on. So for finding J, you could write it this way. I'm going to have negative and then whatever I get of when I do my determinant. So 2 times 3 is 6. Take away from that 5 times 4, which is 20. That's negative 14. I put that right in here, negative 14. That gives me positive 14J. Does that match what we had? Yes? Okay. Does this make sense? And then to get K, what do? Cover up K, and you do determinant on the other two, and that one you don't change the sign. And if you do that, we should get what? What is that? 2 times negative 1. So negative 2 and plus 12, so 10. Any questions? Yes. What? Well, what do you mean? What does it come from? Well, the determinant in matrices, right? With matrices, the determinant is a way to help you find the inverse of a matrix. So in order, you put, if you multiply matrix times like a 2 by 2 matrix by another 2 by 2 matrix, and you want to get the identity, which is the 1, 0, 0, 1 matrix, then you need its inverse. And we use the determinant to get the inverse. I mean, that's the way most people have seen it. But there's lots of them. We're going to use the determinant later to take a 2 or 3 dimensional space and convert it to a different 2 or 3 dimensional space. It'll be a transformation of one space into another, and we'll use actually a determinant. So there's more than one use, but most people at this point have only seen it in matrices for finding inverses. You could plug in the coordinates for 2 different planes, do a determinant, and find a perpendicular. No, it's kind of, it'll be like, I don't want to get ahead of ourselves here, but let's just take something very basic, like if I have a point in 2-dimensional space, I can get there. One way I can get to that point is by walking to the right by x, right? And then walking up perpendicular to the x-axis, walk up straight y. And this is called the Euclidean plane. XY represents distance out the x, y represents distance up. But there's another way to get to that point. Polar coordinates, right? So when you convert from Cartesian coordinates to polar coordinates, that conversion can be done using determinants. The Jacobian, exactly. Yep. So that's what, but we'll be doing it to go like from Cartesian 3-dimensional to spherical 3-dimensional. But that's just later. All right. So that's the mechanical way of doing a cross product. Now, what are the results of the cross product? Because, I mean, all we've done so far is just looked at, hey, it's a mechanical process of putting 2 vectors together. It gave us a vector out, right? It gave us a new vector. And that's the difference between the cross and the dot. So that cross product, it produces this new vector. That vector will always be perpendicular to the 2 vectors you started with. And that's the big, big deal with the cross product at this point. Is that if you give me any 2 vectors, non-zero vectors, and as long as they're not parallel, so 2 distinct vectors, and you cross them, do the cross product, that third vector is orthogonal to both. What does orthogonal mean? 90 degrees. So I have a picture here. I don't know how good this is going to come out. Let me try and zoom in on this. The red vector and the blue vector are just 2 vectors sitting out there, okay? The black vector is the cross product. And if I turn this, you'll notice, hopefully you'll agree with me, that the black one is perpendicular to the red one, right? And if I twist it over this way, you'll notice also, hopefully, you'll be convinced that it's perpendicular to the blue one also. So orthogonal to both. Now, how could we show that? How could we show that the cross product U cross V is orthogonal to U and orthogonal to V? How could we do that?
Take a cross product of a new one and one of the other ones, get back the third one.
Take the cross, say.
So you take the cross product of U and V, and then take the cross product of that cross product and V, get back E.
Interesting. That's an interesting approach. I'm not quite sure that'll work because let me think about that. I'm not sure if that'll work. The dot product is the way to go, though, because what did we learn last class? Yeah, if you take two vectors and you take their dot product, and that's 0, then you know they're orthogonal. So all I have to do here is show that this cross product is orthogonal to both of these. So I'm going to do that. So what was, those are the same vectors we just had, right? Those are the same vectors? So I already know what that cross product is. I'm working example 2 here. My cross product that I did just a second ago, and I did it 2 different ways, came out to be, what was it? -4, 14, 10? Okay. That's my cross product. I want to show, WTS, I want to show that U cross V is orthogonal to U. Now that's a symbol we usually use for orthogonal, perpendicular. So I want to show that that's true. So what I want to show really is that when I take U cross V and I dot it with U, that I get 0. That will prove that I'm orthogonal to U. So if I take -4, 14, 10, and I dot it with U, U was 2, -3, 5, I get, what, -8 minus what? 42 plus 50, and that's 0. So it checks. So I know that my cross product is orthogonal to U, but I'm supposed to show it's orthogonal to both. So now I need to look at, I want to show that U cross V is orthogonal to V, which means I want to show that their dot product is 0. So U cross V is this, and I dot that with V, which is 4, -1, 3. And is that 0? Should be. -16 minus 14 plus 30 is 0. So that just verifies the property that I said we have. Okay, show that U cross U is 0 for any vector in R3. Show that U cross U is always 0. How would you do that? Could I just make up a U, like pick my own numbers? Yes or no? What do you think? U, an element of R3. U, not the 0 vector. If it's the 0 vector, then we should get 0. What's that? It could be unit. My question, though, is this. If you're asked to show something very general like this, that if you take any vector and cross it with itself, right? That's what it's saying? That you always get 0. Can you just pick a vector like the vector 2, 3, 4 and then cross it with 2, 3, 4 and get the result of 0 and be satisfied it holds for every vector? No. It's not good enough. Okay, just because it happens one time does not mean it's going to happen forever, right? Sun came up today, going to come up tomorrow. So even if something happens a million times, it doesn't mean it's going to happen the next time, right? So one example of something in mathematics is not good enough. We have to prove it generally. So what I'm going to do is I'm going to just call U, U1, U2, U3, right? That's a general vector. And now I'm going to cross it with itself. So did y'all like the determinant one, the shorter one? Okay, so what I'm going to do is I'm going to take I, J, K. I'm going to write down the components, U1, U2, U3. I'm going to write down U1, U2, U3 again, because it's the same vector, right? And now let's cover up I, because I'm going to try and figure out what I is over here. Cover up I, and what happens? U2 times U3 minus U3 times U2, which is 0, isn't it? So we get 0. Y'all follow that? Now do J. Now remember, when I do J, I need to put a negative in front of it. So when I cover this up, I get U1, U3 minus U3, U1. It's the same. It's going to subtract and you get 0 again, right? And then for K, I mean, can you see now? K is going to do the exact same thing. So you get 0K. So that is the 0, 0, 0 vector. On my notes, I need you to fix something. Right there. Can you all see that? That needs to be what? That's right. I forgot how I get up there. Oh, whoa. All right. Close that program real quick. There we go. That's the 0 vector, right? You cross two vectors, you get a vector. So that should be 0 vector, not 0, the number. Okay, find a vector that is perpendicular to the plane that passes through these points. This is an absolutely fundamental problem in this class. I mean, this is kind of like you want to run a marathon, you need to know how to put your shoes on, right? This is putting your shoes on. You must be able to take a plane and find a vector that's popping out of that plane, that's perpendicular to the plane. So geometrically speaking, if somebody gives me, in three-dimensional space, if somebody gives me 3 points, well, let's say 2 points would define a line, wouldn't it? It takes a third point to define a plane. In fact, if I put 3 points here like this, I define a triangle. But if you extend that triangle out in every direction, you get a plane, right? So what we're trying to do is we're trying to find a vector that's popping out of this plane perpendicular to the plane. So we're trying to find a vector that's coming out of this that is perpendicular to that plane. This, basically, right? That's all we want. Pencil sticking out of a plane. So how can we do it? Let me label these points here. These are points, right? Not vectors. 1, 4, 6, -2, 5, -1. And does it really matter where I'm putting these? No, because in three-dimensional space, you could be like at different viewpoints. So it really doesn't matter how you label your points. Okay. Yeah, kind of. Yes. You're on the right track, but what we have to distinguish here is, are we given vectors or are we given points? We're given points, right? we can't cross 2 points. We can cross 2 vectors. So what we have to do is we have to create the vectors first. Once we create the vectors, then we cross them. That'll give us what we want, right? So I don't know how many times I've had in the past students will take the points and cross the points, and that's not allowed, right? So what vectors should we create? It doesn't matter. You just need 2 of them, and those 2 vectors have to live on the plane. So how about I do the vector that goes from here to here? I'll call that u. And then I can take any other vector on the plane. It can go from the point here up here. I need to stop going to the board and doing that. From here to this one, right? I could do that. I could do the vector that goes from here down to here. I could do the vector that goes from here to here, or I could go from here to here. It does not matter because remember, the vectors, we can always move them so that they're always tail to tail. And then cross them, no matter what, it's going to pop a vector out that's perpendicular to both. Therefore, it'll be perpendicular to the plane. Y'all agree? So, that's right. Would you agree with this? Given any plane, right? Given any plane, there is a vector that is perpendicular to the plane, right? Now that vector can be moved around. You can change its length, can't you? In fact, you could also even pop it out the other side. But for every plane that's given, there is a kind of a unique direction of the vector that's perpendicular to the plane. Agreed? The length may vary, but the direction of it is either this or that. So we are only looking for one. We can always scale it though, right? You can always scale a vector and it's equivalent to, right, scalar multiples basically are parallel. So, but the cross product will give us what we need here, all right? So what other, whoa, what the heck is all that? What other vector do we want to grab here? You want to do that one? Okay. We'll call that V. So what is U? What is U? That's right. It's the vector, the way I drew it, it's the vector that goes from 1, -1, 1 to -2, 5, -1. So I'm going to make sure I get this right. -2 minus 1, which is -3, right? So I'm doing -2, take away 1, and then 5, take away -1, 6, and then -1, take away 1 is -2. Everyone agree that's U? V? Yes. 0. 5. It's okay. I'm trying to get you to respond. 5 again. Okay. Now we cross those 2, right? We cross those 2 vectors. And that should give us a vector that's going to pop out of our plane and be perpendicular to our plane. Now, if you get real comfortable with this, you can just do your IJK right here, right? And you see you can already kind of cover up your I and do your determinant. What will that give you? $30, take away -10, so 40. I'm not sure if I should associate no response to you got it or no response is you're gone, you don't understand. Are you okay? All right. Look, I know that there are a lot of you who are in, like, you're off at college during the normal semester, you're in for the summer, and you may not be used to an instructor actually asking you if you understand it. But I'm going to ask you if you understand it, all right? So please reply back, because maybe right now you got it, but later on you may not, and I want us to at least have that comfort that we can talk to each other. So are we comfortable with this being positive 40 for our I? Okay. Now J is going to be negative of whatever I get when I cover up J and do my determinant. So yeah, positive 15, because we have to change the sign, right? And then cover up K, Negative 15? Okay. All right, that is a vector that is orthogonal to the plane, perpendicular to the plane. All right? Do you agree that this vector would also be perpendicular? Would that be perpendicular to the plane? Yes, why? Scalar multiple of this, right? I just divided everything here by 3, or, yeah, 5, by 5, and I got that. So that's pointed in the exact same direction, right? It's just shorter. And what about this vector? Yes, it's pointed out the other side, but it's still perpendicular. Now, no one has asked this, but what if you had crossed it the other way? What if you had done V cross U instead of U cross V? So if you did V cross U instead of U cross V, your answer would have come out negative of what you got the other way. So it would have been this. And that has to do with the right-hand rule, okay? Do I say that in here? I'm not sure if I even say that. I should talk about that. The cross product follows the right-hand rule. So let me start a new page. Let me try and draw a three-dimensional space real quick. That's 3D, right? Now, just for convenience, I'm going to say that this is U and that this is V. All right? So we have two vectors, right? Right-hand rule says that as I curl my fingers, right, my thumb points up in the positive Z direction. Right-hand rule is the same for cross products. If I cross U and V, all right, the result of crossing these two, the vector that comes out perpendicular to both, should come out in the direction of your thumb as you go from U towards V. So you can do it also. Where's my pencil and pen? Okay, let's say this is U and this is V. I take these two vectors, I say cross them. Well, we can first put them tail to tail, right, like this. And then if I'm crossing U with V, I go U to V. The result cross product is coming out this direction. If I do V to U, right, V cross U, now I need to put my hand on this side and curl from V to U, and therefore the cross product comes out the other direction. Understand? It's not really that important in this class, but it's just something we should discuss. All right, so we found a vector that was perpendicular. Notice in the instructions I said find a vector. I didn't say find the vector. A meaning there could be more than one, as we saw, but they were all scalar multiples. All right, very important theorem about the cross product. Since the cross product is a vector, we can take its magnitude, right? The magnitude of that vector, the cross product, is equal to the length of U times the length of V times sine of the angle between them. Now that looks very similar to what? The dot product. Last class, right, we had, and since we already had this, we said last class that U dot V is equal to magnitude of U times magnitude of V, cosine of the angle between them. We always said that that angle had to be between 0 and pi, right? This formula is very similar, with the exception that it's the sine function, not the cosine, and it's this side over here you have to take the magnitude, because the magnitude of the vector is a number. We couldn't say up here that a vector is equal to a number, which is what it would be if we didn't have the absolute value there, or magnitude. All right, this is pretty trivial here. Well, maybe not. We'll work through it. We're going to do that problem there. Okay, so I give you that the magnitude of V is 7, the magnitude of U is 3, and the angle between them is 31. Yeah, this is trivial. And I ask you for U cross V's magnitude. So it's just 7 times 3 times sine 31 degrees. That's it. 21 sine 31. That's the exact answer. I need to take that example out of there. It's kind of dumb. Whoa. Damn it. I don't think that that had anything to do with that key problem. I think this thing accidentally touched something up here. All right, next note. Okay, we said that if you take two vectors, right, and you dot them, if the answer is 0, what can we say about the vectors? They're perpendicular. Well, there's something similar with the cross product, all right, but it's not for perpendicular, it's for parallel. So this says that two non-zero vectors, u and v, are parallel if and only if, remember if and only if meant both directions, the cross product is 0. So if you take two vectors, you cross them, and you get 0, they were parallel, right? Or if they're two parallel vectors, then when you cross them, you're guaranteed the cross product is 0. So both directions. Don't confuse the two. Don't think that cross product gives you if you're trying to find a vector that's perpendicular, you're trying to get the cross product to be 0. That's incorrect. Another very, very nice result, and this will come into play later on when we're trying to do surface area approximations. So we'll be trying to approximate a surface area of a surface in three-dimensional space. And to approximate that surface, what we do is we cut up the surface into infinitesimally small little areas. And each of those areas is actually going to turn out to be the area of a little parallelogram. Right there. Do y'all see that? And that's going to be, to do that, we're going to need to know what the magnitude of the cross product is. So what was the dot product again? Did we have a geometric representation of the dot product? Like, did it tell us anything?
How much of one vector fits into the other vector? You're looking at it perpendicular to the vector it's going into, right?
When we said when we did a cross product, if we got 0, what did that tell us? We were orthogonal. Dot product, right? No, did I say cross? Okay, sorry. Dot product told us if dot product was 0, we knew that they were orthogonal. If dot product was positive, what did it tell us? That the angle between them was less than pi over 2. If dot product was negative, it told us that the angle between them was greater. And if dot product was 1, or not 1, if it was u times v, this would be, when they were parallel, the dot product gave us the length of this one times the length of that one. And then this would be the lengths multiplied but negative. So dot product just told us a little bit about the angle between two vectors, right? The magnitude of the cross product gives us something completely useful, all right? It gives us the area of the parallelogram formed by the two vectors. So in this picture here, we have a black vector, which we'll say is u. We have a red vector, which is v. Remember we said that when you take two vectors, you can create this parallelogram? By adding them together, you create a parallelogram? Yes? The area of that parallelogram is actually the length of the cross product. So remember, if I cross these two vectors, right, cross them, it gives me a vector that's perpendicular to both. The length of that vector is equal to the area of that parallelogram. Do y'all see the geometric connection? All right. Now, think a little bit about your take-home exam. There's a problem where I ask you for the surface area of a tetrahedron, right? Let's look at this. I'm going to skip example 6. I'm going to look at example 7 instead. Yes. Let's do this one. I think this is a really good result, okay? Find this area. So I give you 3 points. Are these the same 3 points we had earlier? I did that so we don't have to do as much work. Those are the same 3 points we had earlier, right? Those 3 points formed a triangle in 3-dimensional space. And so I want the area of that triangle, right? Now, the classic formula for area, right, is 1/2 base times height. But you've got to be able to determine the height, right? And the height of this triangle is something like this, and that's going to be difficult to get, right? However, the vectors we had drawn, let me make sure I get this right. I had 1, -1, 1. I had 1, -1, 1. This one was -2, 5, -1. This was 1, 4, 6. I had created 2 vectors. One of them was u, right? And the other one was v. Was there a question? I thought I saw a hand. Is that right? Okay. Yeah. What would the magnitude of the cross product be? Well, what we would have to do is imagine the parallelogram that would be formed by these two. Would look something like this. Oh, that's terrible. That's my parallelogram, right? Those 2 vectors create this parallelogram. I can find the area of that parallelogram by taking the magnitude of the cross product. But I don't want the area of the whole thing. I want the area of half of it, because half of it is the triangle, right? So what we want half of the magnitude of the cross product of u and v. What was the cross product of u and v? Was it like 40, 15, -15, 15? Or, okay, I had it. That was the cross product, right? And I want its magnitude now. So how do you find the magnitude of a vector? Square root of each of the components squared. The numbers are going to get kind of big here. So we have 1/2 times the square root of 1600 plus 225. So someone's going to have to break a calculator out. Let's get a decimal for this. You did the 1/2? You did the square root? 22.6. Any seconds? I need at least 1 second on that. Yes? Okay. 22.6. It would be very difficult to find the area of just an arbitrary triangle in 3-dimensional space with the classic formulas for triangles. The vector formula is much easier. So now I think on the take-home number 5, the tetrahedron, you don't have to get all crazy geometry on that. It's very clean, very simple if you just apply this. I'm giving you way more hints than I normally will here, just to kind of get you through this first test. Any questions? That's right. On example 6, I give you two vectors. You just cross them, take their magnitude. That's the area. Okay, let's move on. 4413. So if we had two vectors, we can create a parallelogram and we can find its area. If we have three vectors, all right, three vectors, then they create this thing called a parallelepiped. Can you see it? It's like these two vectors here, red and blue, create this parallelogram. And then the red and the black create this parallelogram. And then if we just kind of project those across and down, we create this three-dimensional parallelepiped. And that parallelepiped has a volume to it. And the volume of it is what we call the triple product. What it is it's the cross product of V and W. So just take two of your vectors and cross them, okay? That gives you a what? Cross two vectors, that gives you a vector, right? Dot that vector with that third vector. So then take this result, dot it with the other vector. That'll give you a number. Take the absolute value, and that will give you the volume of this. So you could have, instead of doing V and W in here, you could have done U cross W and then had V out here. Or you could have had the W out here and did the V and U inside. It does not matter which way you do it. All right. We can use that to approximate volumes, right? Like infinitesimal volumes. Find the volume of the parallelepiped formed by this. Yeah, you should know by looking at it what they are. If you can't see it, that's one thing. Those are angled brackets. Yeah. So those are vectors. So we have three vectors. What are we going to do for this? To find the volume of the parallelepiped form. Cross two of them, dot it with the other, take the absolute value, which you can do on your own. Okay, one application of cross product in physics is torque. If we tighten a bolt by applying a force to a wrench, then we produce a turning effect. Torque is a vector which represents the tendency of the bolt to turn. Torque is defined to be a vector. The torque vector is R cross F, where R is the position vector of the rigid body of the wrench, basically the wrench, and F is the force acting on the wrench. The direction of the torque is determined by the right-hand rule. Further, the magnitude of the torque is the magnitude of the cross product, which we know by definition is this. Okay, so here's what I've got. Just a little bit of a visual. Imagine, if you will, that we have a bolt here, okay, and this is our wrench, and we've got our hand at the end of the wrench, and we are going to pull in the direction of this vector. Then we are going to create a turning force, right? That turning force can be quantified with the cross product. And so this is us looking from the top, okay? I'm going to pull like this on the wrench, right? Pull this way. And then it's going to turn the bolt and there have a force going in, right? If the bolt is threaded, right? If it's a right-hand thread, there's opposite ones, right? Okay, so right-hand thread, I tighten, it's going to want to go in. So now this is that same picture in three-dimensional space, and you can see the blue vector, it's off the page. is going down. That blue vector going down is the force basically in. Okay? So what happens if I shorten this right here? In terms of torque, are you going to get more torque or less torque if I shorten the force? You should get less. So I think that blue vector, I'm trying to keep it pointing in the same direction. Keep an eye on that blue vector. There it comes. You see? So even though I'm pointing in the same direction, I'm not pulling with as much force. I'm not getting as much torque. Right? What will give me maximum torque? Why?
Because a rectangle is greater area than a parallelogram.
Also look at this right here. Right? Look at your torque. This torque, right, the magnitude of the torque, the length of the torque, the length of that blue vector is the length of the wrench, which shouldn't change. The force, right, the length of the force vector, which if you're going to pull with the same force, right, that should stay the same. And now you're just like, which direction do I pull in to get the most torque? Well, then you want that angle to be as big as the angle to produce the biggest number you can here. And sine is always the biggest when it's 1, right? And what angle gives you 1 on sine? 90 degrees. Sine of 90 degrees. So you want to be 90 degrees. You want the angle between them to be 90, so you want to be perpendicular. Correct. I mean, it's logically, I think we all understand that, but you can see how it connects to the math now, right? So if I move this, if I try and keep it the same length and I rotate it over, that should get longer. See it? Okay. Now what happens if I go and I put the force vector pointed in the opposite direction? Now I'm going to take the bolt out of the, right? I'm loosening it so it's coming out the other direction. And do you see the right-hand rule here? If I slide F down and I'm crossing R with F, right-hand rule comes out. Yes? If I move my F this way, slide it down here, R to F, I would have to be like this, R to F into the page. So, all right, that's it. Remember I said ignore those homework problems? I'm going to continue just to email them to you, all right? There's never homework due to turn in. But I could do like a homework check or something. In fact, I was going to do it today. I was going to walk in, I was going to say, hey, I'm going to walk around to see what homework you did. But I decided I'd wait till next week to do that. To give you at least the weekend to... Well, you have your take-homes due on Monday, right? Okay. Okay, how are we doing on time? This class goes till 4:30? Okay, so we still have another at least half hour before we take our first break. Sure, I'm still recording here. All right, 10.5, equations of lines and planes. All right, preliminary concept. Given two vectors, R naught, I'm going to say R naught, R0. Is that okay for that first one? Given two vectors, R naught, R1. If we compute R1 minus R naught, the resultant vector is equivalent to a vector drawn from the tip of R naught to the tip of R1. So let's just do that drawing and convince ourselves that that's true. So let's say I'm going to orient everything. I'm going to do it in 2D so it's easier to draw. Let's say I take some vector here, call that R naught. I take some other vector, I'll call that one R1. And then I'm asked for us to draw what's R1 minus R0. So this is the same as R1 plus negative R0, isn't it? And negative R0 would be R0 but pointed in the opposite direction, wouldn't it? So it'd be, this is negative R0. Do y'all believe that? Now, how could I add, because this is what this means here, adding, right? How do I add two vectors together? Tail of one to the tip of the other, right? So why don't I take this R0 here, and I'll take the tail of that one, and I'll put it on the tip of the R1. So it'll point like this, won't it? It'll be something like that. That's negative R0. And so the resultant vector should be, we basically travel down R1, travel across negative R0. We end up at this tip here, which means the resultant vector was the vector that just goes from here to here, isn't it? That is R1 minus R0. Do you all see that? But because vectors can be moved around, do you also see that if I move that around and I move it here, it's the vector that connects the tips of the two vectors we started with, R1 and R0. Yes? Any questions on that? Yes. Yes. So go back to the note that I have here written, 10.5 preliminary concepts. Given two vectors, R0 and R1, if we compute their difference, right, the result, the vector we get out, goes from the tip of R0 to the tip of R1. So you see that? It goes, this resultant vector goes from the tip of R0 to the tip of R1. Okay, we need that kind of geometric idea before I proceed to the next part of this. Tail to tail. We oriented them both so that we put both their tails at the origin, right? So because they were sliding around it, right? We brought them back and we brought them tail to tail. So the vector that goes from tail to tail in that drawing is the zero vector. There's no. All right. So now our background with lines, right, is really like two-dimensional y equals mx plus b, right? Old school linear equations. But what we're going to try and do now is come up with a new way of defining a line. And we're going to try and use it, or do it using vectors. So what I want you to see first is that if I have a line that every point on that line has a corresponding vector that goes from the origin to that point, right? Do you agree? Every one of them. I can bring more and more in here. So every point on that line has a vector that goes to it from the origin. The vector equation of a line is an equation which will generate all of those vectors that I just showed you, right? It's something, the vector equation of a line, not the standard scalar equation that we learned in college algebra. The vector equation of a line is an equation that creates all those black vectors, all of them, the infinitely many of them. So here's how we're going to develop the equation. First of all, let us focus on creating just one of these vectors. So let's say we have a point on the line, right? And that point is the point x naught, y naught. Right? There it is, x naught, y naught, right there. Then do you agree that the vector x naught, y naught is the vector that goes from the origin to that point? Yes? So I've got one of infinitely many vectors now? Good. Now I needed a point, didn't I? I mean, I assumed I knew that point on the line, but I created that first vector. Now, let's try to get another vector. So let's say we have another point. So now I've required us to have 2 points. Isn't that what we needed anyway? I mean, to define a line, don't you always need 2 points? Okay. So if I have a second point, call it x1, y1, then I can create the vector that goes from the origin to that point and call it x1, y1. So now we've got 2. We're going to be here all day if we keep doing it this way, right? That's all I should need, though, right? 2 points, I should be able to define the line. So here's how I'm going to create the line. Let's look at the vector r1 minus r naught. Didn't we say the vector r1 minus r naught was the vector that connected the tip of r naught to the tip of r1? Which I drew down here is v. But we can slide that v up, can't we? There we go. So v, what do you notice about v? V is parallel to our line, isn't it? It's a new vector that's actually parallel to our line. So if I look at 2v, I double what v is, I would be out here, wouldn't I? And if I do negative v here, then I'm on the other side. So how can I get the whole line? I want to back up just a second, right here. Look, if I want to get to this point right here, right, all I'd need to do is know what R0 is, and then add to it what? V, and I would be here, right? So I would be at a point on the line. If I wanted to get to this point, or another point, I could go out R naught, and then I could go twice V and be here. If I wanted to do another third point, I could go out R naught, and this time go negative V, and I could have another point on the line. So how do I create all of them? I take R naught, right? Ignore this for a second. I take R naught, that vector, and then I add every multiple of V, right? Every multiple should take you out in one. All the multiples that are positive should take you out in one direction. All the multiples that are negative should take you the other direction. So this is pretty much it. Now look at our notation here. R of t, it's a function. It's what we call a vector function because we don't use f of t because it involves vectors. So we use the vector notation on the r. R of t equals r naught plus tv. Here t is a scalar, and v is what we call the direction or direction vector of the line. So this is me scaling that v. That's R naught with all the little scalars. And notice I draw everything. So in two-dimensional space, R of t equals R naught plus tv is our vector equation line. T is a scalar, v is a direction. We have to know what R naught is though, right? R naught is always going to be given to us, or we're going to have to extrapolate it somehow, but that's always going to be our initial point. And then the direction, right, is going to be that vector that points in the direction of the line. So if you go back college algebra, what did we need to define a line? 2 points, or you could also have a point and a slope, couldn't you? And this is kind of like the point and slope. We need a point, and then we need a direction vector in order to define the vector equation of a line. So going in here, if I replace R naught up here with x naught, y naught, I replace v with, we'll call v ab, since it's a vector, 2 components. Then we get this. We distribute our t through and add the 2 vectors together, we get this. Therefore, the components of this vector equation are this x component and y component, and here they are. And these two equations are called the parametric equations of the line. We also call the A and B the direction numbers. And finally, if you take these parametric equations, couldn't you solve each of these for t? How would you solve this one for t? Take x naught over to the other side, divide by a. Over here, take y naught to the other side, divide by b. Then they would both be solved for t, wouldn't they? So you set them equal to each other, and you get what are called the symmetric equations. So we have several different variations of equations of lines. We have the vector equation of the line, which is basically up here. We have the parametric equation of a line, which is here. And we have the symmetric equation of a line, which is here. Everything that we just did extends to three-dimensional. So if we have some initial vector that points to some point on the line in three-dimensional space, and if someone gives us a new direction vector, this time it's ABC instead of just AB, then we can define our vector equation the exact same way. And that'll give you three parametric equations, and it'll give you your symmetric equations will actually have three equations. There's a lot of information there. I'm running through it fast, but you've got a copy of it. Let's see if we can kind of get to work on some examples. I do need to talk about this part, but you know what? I think I'll skip this and we'll deal with it as we get to an example. This 10.5.12. The idea in 10.5.12 is that sometimes we don't want to draw the whole line, we just want to draw a segment of the line. So there's a way that you can constrain your t so that t doesn't go through all numbers and it just draws part of the line you want. So we'll deal with that when we get to it. All right, the points 3, 6, and 7, 4 lie on a line. Find the vector equation of this line. Find another point on the line. Find the parametric equations of this line. Find the symmetric equations of this line. Do y'all have that? Yeah? You're looking at your notes kind of crazy there. You okay? Okay. All right, so here we go. I have 2 points. Okay, part A. What's the vector equation of the line? Well, the vector equation of any line is R of t equals R naught plus TV. When I was in college, my professor used this instead. I don't know if you've seen this before. Maybe you've seen that. I remembered it better this way. The only difference is that when I learned it, we used U here instead of R naught, and it's what we call the couch potato formula, right? U plus a TV. That's U and a TV. Couch potato, right? It always stuck. But this book that I'm using here uses R naught, so no go there. All right, let's start with that. Do we have R naught? Where does R naught come from? R naught is a vector, right? But it's actually the vector that goes from the origin to either one of the points on the line. So I get to choose. I can use 3, 6, or 7, 4. Now, when I write it in here, I have to write it in a vector form. So angle bracket, I'll use 3, 6, plus t times v. But remember, what was v? Not distance. It's the vector that lies on the line, right? So it's the vector. You could use the vector that connects the 2 points together, couldn't you? Right? That v has to lie on your line. So why don't you just come up with the vector connecting those 2 points? So v here comes from, does it matter which way I connect them? No, I can go either way. But I'll go, I'm going to go from here 2 here, all right? So that should give me the vector 4, 8. All right, I do 7 minus 3, it's 4, and then 14 minus 6 is 8. So that's my, what do we call that? The what? That is the result. But in terms of the vector equation of the line, this is the direction vector, okay? That's our direction vector, 4, 8. So I come in here, 3, 6 plus t times 4, 8. I should also state here that t is an element of the real numbers. I'm just going to stress here that, look, to create the entire line, I need t to be a scalar, and that t needs to vary through everything. What if t is 0? Then you have a vector, don't you? And it points to that point 3, 6. Y'all see that? What if t is 1? T is 1, then you're just adding these two vectors together, right? Which gives you what? 7, 14, which points to that one, doesn't it? But then you take all the multiples and you create the line both directions. All right, now this is the vector equation line. We need to kind of clean it up. Let's distribute the t through. Can we add these two vectors together? How do we add vectors? Add their components, right? So what's 3 plus 4t? 3 plus 4t, right? I can't add them. They're not like terms. So 3 plus 4t, and then the other one is 6 plus 8t. So that is it. That's the grand finale of our vector equation of our line. Right there. That answers part A. Part B. Find another point on the line. How would you find another point on the line? What's that? Plug in a value for t, right? But don't use 0 and don't use 1, because 0 we already said gave us a point we already knew was there. 1 gave us the other point. So we got to pick something else. So how about r of pi? No, we won't do that. Just r of 2. How about that? So what would that give us? 11. Is that right? 8, 9, 10, 11. Yeah. 16. R of 2 would be 1122. And so technically, the point on the line would be the point 1122. This is a vector that points to that point, right? So that is another point. Now, you could have different answers depending on what you use, right? I just chose 2. You could have picked -2, 3, 5, pi, e. Okay, part C. Find the parametric equations of the lines. So parametric equations, since we're in two-dimensional space, we should have an equation for x and an equation for y. And these are very, very obvious. Once you've gone here, these are your two equations, right? This is what x is. X depends on t, y depends on t. So you just put those two here. Those are your parametrics. And then, part D, symmetric equations. So how do we get symmetric equations? We solve these for t and then set them equal to each other. So if I solve that first one for t, I get x minus 3 over 4 equals t. If I solve the other one for t, I get y minus 6 over 8 equals t. And now you set them both equal to each other, so the main result here is that x minus 3 over 4 must equal y minus 6 over 8. Any questions on that? you might notice something here. When you have your, what do we call these? What do we call this? This is symmetric, right? These are the parametric equations. This is a symmetric equation. When you look at the symmetric equation, notice that the denominator 4 and 8 are actually the direction numbers, right? What was the direction vector? It was 4, 8, wasn't it? This 4 and this 8 are actually, it will always turn out to be your direction numbers down there when you do your symmetric equations. You think you could extend this out into the next example where you're in 3D now? Or would you like me to work it? I'm talking about 10.5 example 2. I don't mind working it, but you just let me know. Yes, work it? I tell you what I will do. Let's skip example 2. I will do it after I do example 3, because I want to make sure I get example 3 before we take our break. All right, so example 3. Determine that these lines are skew. That is, that they do not intersect, and they are not parallel, and they are not orthogonal. And I give you 2 lines. Now let's just look first of all about, the way I wrote out the lines. I gave you L1, meaning line 1, and then I gave you angled brackets, and I gave you these 3 components, right? This is basically the vector form of the line. I just didn't write R of t in front of it. And then down here, same thing, and I used a different variable. Why do you think I used s instead of t? They're 2 different lines, right? They are 2 different lines. And I want to know if these 2 lines hit each other, right? Or if they don't. I mean, it could be. We're going to show that they're skew. But we do have to show that they don't intersect each other. So let's say I have a line sitting out there in space, and I have another line sitting out here in space, and let's say they do hit each other, right? Do you agree that at every point on this line, there's a t, right? A t that gets you there? Yes? And then every point on this line, there's a t that gets you that one? Does it have to be the same t for both lines, like this point where they hit? Does it have to be the same t for both? No. So I need to not call them t in both lines. One of them I'll call t, the other one s. So s controls this line, t controls this line, and I want to know if there's an s and a t that when you plug something in for s, you get to this intersection, and some other value of t gets you here also. It's a little subtlety, but it's important. If you put t for both lines, you probably wouldn't be able to get the answer. Even if they did intersect it, you wouldn't be able to find it, because the t wouldn't be the same for both. Does that make sense or not? You can almost look at it like a fly going through the room, or let's say a bullet going through the room in a straight line, right? And then another bullet going through the room in a straight line. Let's say their paths cross each other. Does that mean that the bullets had to hit each other at the same point in time? No, right? You could have bullet go through, and their paths crossed, but they weren't at the same place at the same point in time. Same thing with these lines. We can draw the line by varying the value of t, and we can draw the other line by varying the value of s. Yay or nay? Okay. How are we going to do this? I'm gonna start labeling things. I'm going to call R1 of t is equal to this first one, 1 plus t, negative 2 plus 3t, and then 4 minus t. And then the other one I'm going to call R2, and I have to use s, not t. 2s, 3 plus s, negative 3 plus 4s. All right. Help me out here. Maybe we should start with the easier things here. What do you think is the easiest? We have to show 3 things. They don't hit each other, they don't intersect, they're not parallel, and they're not orthogonal. Which of those 3 seems the easiest to you? What's that? Okay, so yeah, let's go with that. Let's go with, let's try the orthogonal first, because that was dot product, wasn't it? And that's the first thing we learned. So what would I need to dot, though? What am I dotting? Think about this. We have two lines, right? That's it. This is the R1 line, right? It has its own direction, doesn't it? That direction vector that we have on this we called V, right? I'll call it V1. Remember that? We had R naught, which got us up to the line, and then the V was the direction. Yes? Then we have some other lines sitting out here. R2. And it has its own direction vector. It's not the same as the other direction vector. Well, maybe it is if they're parallel, who knows. But we'll call this one V2. Well, we will do something like that to see when they intersect. We're checking for orthogonality, right? Are they orthogonal? We're in three-dimensional space, right? 3D. Are these two orthogonal? I'm trying to... No? Right? They don't look orthogonal to you, right? Okay. Are they orthogonal now? Yes, right? Orthogonal does not mean they have to hit each other. Orthogonal means the directions are perpendicular, right? So when we're looking at these lines, if I want to know if they're orthogonal in three-dimensional space, I want to know if their directions are orthogonal, right? What is the direction of R1? What is the direction? Can you tell? Is this the direction of R1? Is the whole damn thing the direction? No. It's only certain pieces of it, right? Which parts? It's the coefficients of t. Remember where that came from. We had the general idea. R of t was equal to R naught plus TV, right? The t distributes through to the v. The v was the direction, right? So the numbers in front of t are the direction, or are the direction numbers of our line. So what is the direction of R1? So I'm going to call it V1. What's its direction vector? 1, that comes from here. 3, right? You don't need to write the t in there. And then -1. What's the direction of the other line? 2, careful, 1, right? And then 4. Does that make sense? Now let's check for orthogonality. So dot these. What's V1 dotted with V2? Checking this, right? I'm checking the orthogonality. I do V1 dotting with V2. This gives me, what did you get? 1? But that's not 0, right? They're not orthogonal. Agreed? You dot them, you get a number other than 0. So I can tell you right now, these lines are not orthogonal to each other. How can I check for for parallel? Cross product? What do y'all think?
You could do the dot product, and then the answer is equal to the magnitude of one of those vectors, and then be parallel. But that'd be more work.
Yeah, I hear you. But I even think the cross product might be more work. Are they scalar multiples? Right? If two vectors are parallel, right? If the lines are parallel, that means that their direction vectors must be parallel. And for direction vectors to be parallel, we just need them to be scalar multiples. So are these two scalar multiples of each other? No. Right? So we don't even need the cross product. In fact, very rarely have I ever used the cross product to check to see if two vectors are parallel, because you can always check to see if they're scalar multiples first. So for checking parallel, we usually write that for parallel. To check parallel, I noticed that if I take the vector 1, 3, -1, it is not a scalar multiple, so I'm using C of 2, 1, 4. It is not a scalar multiple, so not parallel. Therefore, not parallel. Therefore, not perpendicular. How did I say you could check to see if two things were scalar multiples, two vectors? Common factor, but I said you could also just take a ratio of the components. Like, what's 1 divided by 2? It's 1/2, right? If these are scalar multiples, then that ratio must hold true with all components. So if this is 1/2, this would also have to be, what? This would have had to have been 3 over, that would have to have been a 6. Okay? So you have to maintain that ratio the whole way. That's a very easy way to check it. All right, so now the hardest part of it is, are they skew? I mean, do they intersect? So if they intersect, right? If they intersect, then there exists, a backwards capital E means there exists an S and a T such that R1 of T equals R2 of S. Does that make sense what I just wrote? If these lines hit each other, yes? It means there exists. There exists. Yes, well, if the two lines hit each other, there is a common point. But because these are vector equations, I use like a running time, right? T is almost like time. I use a time to draw it, right? T starts to vary, I start to draw the line. S starts to vary, I start to draw the other line. If they hit each other, there's some T and there's some S where my vector equations are the same. They hit each other, right? Remember, these vector equations draw vectors, don't they? They draw vectors. So if they hit each other, there's some point in time T, and there's some other point, or some point in time S, where they draw the same exact vector, pointing to the same exact place. Right? But that just means that (1 plus T, -2 plus 3T, 4 minus T, that's R1 of T, right? Must equal R2 of S, which we said was 2S, 3 plus S, -3 plus 4S. What is the only way that two vectors can be equivalent? Their components have to match, right? This component has to match that component. This component has to match this component. This component has to match this component. Well, guess what we have there if we do that, if we match the components? We have a system of equations. 1 plus T must be equal to 2S. The other one is -2 plus 3T must be 3 plus S. And the last one is 4 minus T must be equal to -3 plus 4S. And I'm going to put a brace on the outside to stress the fact that I have a system of equations. I need to find the S and T that make all three of those true simultaneously. How many equations do we have? 3, how many variables do we have? 2. We should get a unique solution. You have more equations than variables. Whenever you have more equations than variables, you can usually solve. If you have more variables than equations, you can get general solutions, but you can't get exact solutions. All right, so how would you want to go about that? Okay, so you said the word. You could use substitution, right? Or you could use the other method, which is called elimination. Or if you're really technology, into technology, you can use your calculator to do matrices and do like a reduced row echelon form on your calculator, and you can solve it. I will expect, well, at least in Cal 2, I expect all my students to be able to use a calculator to do solving systems of equations. You remember in Cal 2 you did like partial fraction decomposition to do integration? Remember that? You would do, break down something, and then you get a system of equations. And sometimes you would have like 6 variables, depending on your instructor, right? Depending on how far they went with it. Sometimes it was just 2 or 3 variables. Sometimes it was 5 or 6. If you had 6, then you go to a computer for that, for help. So anyway, either way, I don't care here how you do it. Let's take our break. Okay? I'll solve that on my calculator real quick, and then that way it'll influence you to figure, either you got to figure out how to do that on your own, or you need to come to me and I can help you with your calculator. All right, we're going to take a break. I've not forgotten example 2. All right, we will talk about that. Let's say it's 242. We'll say 253. We'll be back here. I've decided, yes, I'm going to work through the rest of this. So remember, what we're trying to do is find a t and an s, if it's even possible, that would satisfy all 3 equations at one time. So one way we could do this is we could solve the first equation for t here. All right, so I'm going to choose substitution instead of elimination. Solve that for t. We get t is equal to 2s minus 1. Okay, that's what t must be. And then I'm going to take my second equation. I'm going to replace t with that. Negative 2 plus 3 times t, but t is 2s minus 1, equals 3 plus s. And that equation has just s in it, right? So I should be able to solve that for s. So we get, I'm continuing here, negative 2 plus 6s minus 3 equals 3 plus s. My s's and my 5s are not good. They look too similar. Those are the only ones I really have problems with. Everything else I've got down, but all right, back to this, sorry. What does this come out to be here? 5s equals 8, is that right? S equals 8/5. Do y'all agree with that? All right, so now if S is 8/5, then let's go back up here and let's figure out what T is. T is equal to 2 times S, so 2 times 8/5, minus 1, which is 16/5, minus 1, which is 11/5. So it may appear at this point that I have actually found an S and I have found a T that satisfy the equations. The problem is that I must satisfy all 3. All 3 at the same time. So I need to be able to plug these two values into this third equation, which I haven't even looked at, and it needs to be satisfied. So let's try it. Checking it into this one. 4 minus t, which is 11/5, equals negative 3 plus 4 times s. What's 4 times s? 32 over 5. Well, what can you say here? 9/5. Yeah, those aren't true. That is not true. So I found a t and s that made the first two true, but not the second. First two, but not the third. So it's not possible. All right, inconsistent system here. That means they don't intersect. So therefore, the line is skew. Not orthogonal, not parallel. They don't intersect. Any questions on that? Okay, I said I would do example 2 real quick. I'm going to pass around the sign-in sheet. So going back to example 2, we had the point 3, 6, negative 4. Had the point 7, 14, negative 7. Part A says find the vector equation of this line. Vector equation of any line can be written R of t equals R naught plus TV. Do we know R naught here? What's R naught? Yeah, we got a vector from the origin to one of those points. So we'll take 3, 6, negative 4. We'll make a vector out of it. Plus, now we need t times what? A direction vector. The direction vector is a vector that lives on the line. Therefore, it should be it's not the vector going from the origin to 7, 14, negative 7. It's the vector going from where to where? The one point to the other, right? So what's a vector going from one of those points to the other? We'll go from this one to this one. 4, 8, negative 3. Everyone got that? Now at this point, I can distribute through with my t. Does anyone have a question at this point? Put these together. Add them component to component. And by putting it all together like this, what's kind of staring at you now? What can you see? Right, when you get it down to this form, what's also kind of glaring at you here? Am I the only one? The parametric equations are right here, 1, 2, 3. But that's part C. Part B is we need to find another point, right? Oh no, I didn't ask you for that, did I? Oh, I didn't. I'm sorry. So part B, yeah. What are the parametrics? So the parametrics are x, y, and z. Why is it x, y, and z in this problem, and the one before was just x and y? We're three-dimensional, right? Okay, so they are 3 plus 4t, 6 plus 8t, negative 4 minus 3t. Part C. Part C, find the symmetric equations. So what do we do for that? Solve each of them for t, set them equal to each other. What's the x the x1 solve for t. What is that? X minus 3 over 4, right? That's going to be equal to t, but t is also going to be equal to whatever this is solved for t. So what's that second one solved for t? Y minus 6 over 8. But that must also be equal to the other one with z solved for t, which is what? Z plus 4 over negative 3. So now your symmetric equation here, there's actually two equal signs here. This must be equal to this, must be equal to this. Questions? Part D. So we have this line in three-dimensional space, right? We had 2 points, but we found the equation of the line in general, the vector equation. Part D says, where does this line intersect the YZ plane? Well, what's the YZ plane? The equation of the YZ plane is, what is it? YZ plane is actually, the equation of that is x equals 0, right? Which means you need, for your line to hit the YZ plane, at some point the x has to be 0, right? So go to your parametric equations. Your parametric equation has x in it, doesn't it? So if you take that parametric equation, x equals 3 plus 4t, you replace the x with 0 so that you can force it to hit the x equals 0, the YZ plane. Then you can solve that equation for t. And you get negative 3/4 equals t. Right? Is that the answer? What did I ask for? Find where this line intersects the YZ plane. Does this tell you where it hits? No, it just tells you kind of when it hits. I mean, I know we're not talking about time, but it tells you, it's giving you the t value that you need to plug into the vector equation in order to generate the point. And that point will lie on your YZ plane. So now what I'm going to do is I'm going to go and I'm going to say, what is r of negative 3/4? And what is that? So I've got to go back up and take a look at r. R was right up here, right? Okay, so what do we know happens when we plug it into that first component there? It's 0. Okay, that's what it should be. And then plug in negative 3/4 right here. What do you get? 0? Y'all agree? And then plug it into here. What do you got? Some weird fraction? So you have negative 4, and then it'll have plus, is that 9/4? Get a common denominator, put it together. What do we have there? Negative 7/4. There you go. That's the point at which you hit the the YZ plane. It's actually just it's a point on the z-axis, right? It just coincidentally turned out that that one was 0. Does that make sense? Well, that's a great question. I wouldn't count off for it, but I mean, technically, I guess when I ask when, where, you should put it as a point. But, I'd say like 99% of what I asked for is there. All right, questions? So let me give you something that's more like the types of problems I like to ask, all right? Now that we've kind of developed all of this. I'm going to go to my I'm going to try and integrate a little bit of your homework into this. Okay, here we go. Find vector equation of line through center of sphere x squared plus y squared plus z squared minus 2x minus 4y plus 8z equals 15, which is perpendicular to both R1 of t equals t 2 minus t 3t and R2 of t equals 5 minus 4t 2t 5. That's more like a problem I like to ask. Okay, we've done everything pretty much, we've talked about everything we need to do this problem. It's just a question of can you put it all together now? All right, you ready? All right, I'm going to let you think about it for about 5 minutes. I'm going to take a little break. I'm going to let you think about it for about 5 minutes, maybe 10. You can talk amongst each other. What I'm going to ask for when I come back, I'm going to ask each table if they have a plan of how to go about this problem or not. Okay? Does that seem fair? I don't want you to necessarily start working it out, but more importantly, try and think through how you would approach it. Okay? Okay, let me stop you for a second and talk a little bit about the goal of a problem like this. I'm going to ask in a second for a table to volunteer their approach. And one of the things that I'm going to grade when I take your take-home exams and look at them, one of the things that I'm going to be grading is communication, okay? I get a lot of students that are very good at doing the math, and they just do the math, and then they just get the answer, and there it is. But when I read it, I'm looking through their work, it's not clear how they're going about it, their approach. And what I want you to get good at is writing down how you are attacking the problem. Think about in 2 years, you go and you pull your work out, and you want to make sense out of it. If it's just a bunch of computations, it's going to take you a long time to figure out, why did I do that? What was I doing there? You know? Whereas if you lay it out step-by-step, meticulous, in sentences, writing down what you're doing, then you can always go back and look at it and reference it. So I want you to become better at writing math down. It takes time to get good at writing math down. Understand? So any table feel pretty good about their approach right now? Want to volunteer? We got two? Okay. Whoever wants to, get up on the board right there. And I want you to write out the approach. You can take a minute to think through how you want to do that, okay? Whatever group, whatever else table wants to do it, just go to the board, take a marker, and write out what your approach would be. And I'm not asking for you to be very meticulous now, just a general blueprint of how you're going to attack the problem. While they're writing stuff down, I'm going to come around and see if y'all had any. Let me pause my video so we don't record this. If I have to use foul language or something. Help out. Okay. Can we kill one of those lights? Middle one, I think? Yeah. All right. When I'm starting a problem like this, first thing I ask myself, what am I trying to find, right? What are you trying to find? The vector equation of a line, right? So I'm going to start off by saying I want to find R of t equals R naught plus TV, right? I need to complete this equation, which means the only thing I need, right? The only thing I need for the equation, vector equation of a line, are two things. What are they? A point on the line will allow me to generate R naught, right? And I need a direction of the line. Those two things are the only things I need, right? Two things. So first thing I'm going to try and find is R naught. R naught will come from any point on the line, right? Yeah, but the problem itself says the line goes through the center of the sphere, right? So for R naught, I will find the center of the sphere. Now to do that, I will need to complete the square. Right, this problem right here, x squared plus y squared plus z squared, all that right there, is actually one of your homework problems. Is number 13. So you go through the process of completing the square, and you can get it to look like the formula that, what was your name? David, that's right, David. That David put up there, and from last class, equation, general equation of a sphere, x minus h squared, you got the rest, whatever. Find the center of the sphere, right? That center of the sphere will be h, k, l, right? And from that, I will create R naught, which will be the vector h, k, l. Agreed. Okay, so I've got R naught if I can do that. Now, to get v, I need to understand that v is the direction of this line, right? The line that I've got sitting out, this, sticking out of the center of the sphere. Here's my sphere, here's its center. My line is coming out of this, and it has a particular direction to it. That direction to it, or the direction to of that line, has to satisfy that it is perpendicular to these two lines, right? perpendicular to two different lines. Well, every line has a direction, doesn't it? So I have two lines, R1 and R2. Whatever their directions are vectors. And I need to be perpendicular to both. Well, if I have two vectors, how can I find another vector perpendicular to both? Take the cross product of those two directions. It doesn't need to be unit. Nope, doesn't need to be unit. Does that make sense? These are the connections you have to make for a problem like this. The direction of the line you want is dictated by the fact that you have to be perpendicular to two other lines. So for the second thing, for V, for the direction, V must be perpendicular to V1. What do I mean by V1? What's V1? That's the direction of R1, isn't it? Using the same notation I've been using today. R1 is line 1. V1 would be the direction of R1. And I also need, what's the mathematical symbol for and? Y'all seen these? This and versus this one. Which is which? And is the second one, or is the first one. But we also use commas to represent and. So if you just write a comma, it's okay too. So V must be perpendicular to V1, and V must be perpendicular to V2, the direction of line 2. Therefore, V can be equal to what? If V has to be perpendicular to two different vectors, then I can just define V to be their cross product, right? V1 cross V2. That's the power here of the cross product. It always generates a vector perpendicular to two other vectors. All right, and then you have to go work it out, right? So let's just say that the center of the sphere completely the square. Did anyone do that? Anyone get the center? Okay, so let's say this part right here, finding the center of the sphere, you complete the square and you get, what did you say again? 1, 2, and -4. Anyone else get that? Okay, so that's your center of your sphere. Now, what's V1? What's the direction of line 1? So remember, it's just the coefficients in front of the variable, right? It's not the entire vector equation. It's just the direction numbers. So V1 is 1, -1, 3. And the direction of line 2 is -4, 2, and 0. Since there is no t there, it's really like a plus 0t. So 0, -4, 2, 0. And now I will cross the 2. So I'm going to throw the I, J, K in there. And I'll figure out what I, and then remember it's going to be -J and then K here. So what's I? So I do my little determinant. 0, take away 6, so -6. We find J, which is 0, take away -12, which is +12, but then change it. So it'll be minus -12 here. And then K, 2, take away 4, -2. Are we okay with this or not? So V1 cross V2 must equal -6, 12, negative 2, right? And because, or I can scale it, and just, right? It's okay to scale it. They're all divisible by 2. So I could, you don't have to do this step, but keep my numbers small. So now I have V, don't I? I have a direction vector. I have R naught, which was the vector corresponding to that point. So my final result would be, try and keep it all on one page here, R of t is equal to, let's see, my R naught and then plus t times v. I'm going to put them all together at one time. Is that all right? You understand? I'm just putting it all together. Was that too much? So here was R naught plus TV, distribute the T, collect together, we get this. That is the line that goes through the center of that sphere and is orthogonal to both the lines that were given. What do y'all think of that? See, I mean, it requires a little more thinking than just, here are two vectors, find the cross product. But do you see how all the ideas are there? I mean, all the ideas are underlining that? Yes? I don't know. I was trusting other work. It's 1, 2, negative 4? Okay. That's what I'm being told. I can go and take a look at your work at the end if you want. The answer's probably in the back of the book, so I can check it, but we'll just trust. How many people got 1, 2, negative 4? So we'll go with that. All right, let's move on. Planes. Not the kind in the air. We've already talked a little bit about planes, haven't we? Talked about planes? The ones like the XY plane, the YZ plane, and then we talked about like X equals 2, Z equals 4, things like that. We have seen, though, that to define the vector equation of a line, right, a line, we need a point on the line and a direction vector, or someone could also give us 2 points on the line. We could still get it. We now focus our attention on defining a plane. We can see below that to clearly define a plane, we would need 3 distinct points, right? So I'm going to do this construction. Okay, can you all see the plane okay there? There are 3 points on that plane. If I take I pick some of those points and I create vectors, right? Those vectors go from the origin to those points, right? Then for each point, I have a corresponding vector. If I now look at going from one of those points to the other points, I create these 2 red vectors, yes? And then, if I do the cross product of those red ones, I get that purple vector, which is orthogonal to the plane, right? Everyone agree with that? See it? Okay. So let me go back up here and read through this. We can see below that to clearly define a plane, we would need 3 distinct points. For each point, we create a vector. Then we find 2 vectors, the red ones, which go from one point to the other. Notice that if we cross them, we get the purple vector. It's orthogonal to every line vector in the plane, and therefore is orthogonal to the entire plane. We call this the normal vector to the plane. Right? That's a normal vector to the plane. It is orthogonal to any vector that lives in the plane, right? No matter what vector you ever pick that lives in that plane, that purple vector is orthogonal to any of them. It turns out that in order to define a plane, all right, all you need is a point on the plane and any normal vector to the plane. I mean, this is a pretty big deal, because what did we need for a line, right? For a line, we needed a point in space, right, and then a direction. That's how we found the vector equation of a line. Turns out to find the equation of a plane, you would think I'd need 3 points, right? Or maybe you think I need a point and 2 vectors on the plane. But you don't. You only need a point and a single vector that is normal to the plane. So if I put a point out here in space, there are infinitely many planes that go through this point, right? Infinitely many planes that would go through one point. But to lock a plane in, all I need is for someone to give me a point and then give me one vector that's orthogonal to every vector on the plane. So if I lock this vector in, say that's my normal, then there's only one plane that's perpendicular to that line, to that vector, right? There's only one. So it seems like that's the minimum amount of information we would need to define a plane. All right? So if x naught, y naught, z naught is a point on the plane, and n, the vector n, a, b, c, those are the components, is any, I say any normal vector because we know that the vector pointing out, we can scale it. We could have it point the other direction. So if it's any normal vector to the plane, then the equation of the plane is given right here. Okay? That's the big equation for planes. A, x minus x naught, plus b, y minus y naught, plus c, z minus z naught equals 0. What you will notice about this equation, hopefully you notice, is that this equation is not a vector equation. All right? It's just your normal scalar equation of a plane from back in college algebra, perhaps, when you were talking about planes. There is a vector equation for planes, but we will not see it until almost the end of chapter 13. All right? So we got a ways to go before we talk about it. So there is a way to define a plane in terms of vectors, but we're going to look at this one. Now what's the A, the B, and the C right here in this equation? The A, the B, and the C? Yeah, those are the components of the normal vector, right? And then we have x naught, y naught, z naught. That's the point, not center. That's the point on the plane, any point on the plane. So you give me the point, you give me the normal vector, I give you the equation. Now, if we distribute through, so if we distribute the A through here, if we distribute the B through here, if we distribute the C through here, then we get this, right? This piece right here should be a number, shouldn't it? These last three terms. A is a number. X naught is a number. It's a point, right? Part of the point. This is a number. This is a number. They all have negative signs on them, at least the way it's written up there. And so if we define this piece right here to be D, we call it D, then the equation turns into this. And that might be something that you're more used to seeing back in college algebra, right? If you have something like 2x plus 3y plus 5z plus 10 equals 0, everyone was supposed to know that's the equation of a plane, right? 3 variables, all linear. You have an equation with 3 variables, they're all linear variables, then you have a plane. So let's try this one. We're going to find the equation of a plane that goes through those 3 points. So my points are 1, 2, 14. The other point is -2, -5, -1, and my last point is 12, -3, and 1. Thoughts? Thoughts? Those are 3 points on a plane, and I want the equation of the plane.
If you take the cross product of two, and then use one of them as a point, and then just plug it in your formula here.
Kind of.
Is that what you're asking for?
Kind of. Well, no, I mean, there's only one thing that you said that I don't agree with.
Oh,
You said take the cross. Yeah, you can't do that. That's right. Okay, there you go. So we have the 3 points on the plane, right? It's a triangle, but it extends everywhere, right? We create two vectors, right? We cross those, we will get a normal vector, and then we already have a point, don't we? We have 3 points. We can pick any of them. Got it? So I'm going to just call this x naught, y naught, z naught. Okay, let's just define these vectors. I'll call this one v1. I'll call this one v2. And let's just let this point be 1, 2, 14. We'll let this one be -2, -5, -1. We'll let this one be 12, -3, 1. So what's v1? -3, -7, -15. Uh-oh. What's v2? 11, -5, -13, right? The normal vector of our plane has to be orthogonal to both of those, so we cross them. And this is where your calculator would come in real handy if you had a cross product function on your calculator. Or you could cover up the I, right? Cover up the I, say this minus this, and then you can do that. It's just a little more work. I should have these all worked out, but I don't. I should just have the answer readily available. Who has a TI-89 or something like that? You know how to do cross product on there? Yeah. All right, hit that middle light real quick. Okay, so catalog. See, hold on. Math menu. Meanwhile, someone else is doing this, right, by hand. If you go to math menu, where is it? Matrix, no. Matrix. Vector operations, cross product. And then you put in, let me mess with it first because I don't remember the syntax on this. Okay, I got it. I'll leave it on the screen so you can see how I did it. Okay, 16, you can read it to me. Anyone else get that by hand? Yeah? Okay. So there we go. That's our cross product. So that's our normal vector. That's our A, our B, and our C. We already have our x naught, y naught, z naught up there. So using the formula A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0, we will have 16 x minus what? I already picked it up there for us. Can you hit that middle light again? I'm sorry. Everyone see where that's coming from? 16 is A, x minus x naught. X naught, I had 1, plus B, but that's negative, so negative 204. Y minus y naught is 2, plus C, 92, times Z minus Z naught, so minus 14, equals 0. Well, I can make sure I typed in the vectors correct. I know the calculator did the cross product. 11, 5. Yeah. Yeah. Negative 204, 92. Yeah. Yeah. Negative. Yeah. Okay. So this is the equation of the plane. All right. Now what we could do is distribute 16 through, distribute 204, negative 204 through, distribute 92 through, collect all our constants, blah, 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 but we won't even go. I mean, I would expect that on a test for you to take it the rest of the way, but that's good enough there. I think we've exhausted the idea here. All right. Any questions? If somebody gives you 3 points on a plane, you can find the equation of the plane. Yes? That's right, just one. You could have used the other ones though. Like if you would have wanted, if you chose to, you could have called x naught negative 2, y naught negative 5, and z naught negative 1. But you can't pick pieces of each one. Yeah. All right. Next idea. All right, this is a good little, not a good little, a big concept. The angle between two planes. So now we have two planes, right? And assuming that these two planes were intersecting each other, then we can find the angle between the planes by looking at their normals. So let me just put the normals of each of these planes on here. Can you tell that the green one, well, it's supposed to be, you can't really tell that that's green. Now you kind of can, right? Do you agree that this green one is orthogonal to this plane? So that green one is a normal vector to this plane. And we had a formula that gave us the angle between two vectors, didn't we? It was arc cosine of u dot v over magnitude u magnitude v. That's exactly what we will do. But first we have to convince ourselves visually that if you're trying to find the angle between two planes, you only have to look at their normals. So that's the normal of one plane. Then that orange one is the normal of the other. So whatever the angle between the planes is equivalent to the angle between the normals. And what I can do is I can slide those normals together, and then hopefully you can convince yourself. We have to get some relative position here. Hold on. Ugh. That's as good as I'm going to get it. But the angle between these normals is the same as the angle between the planes. So it's just a visual thing. I mean, isn't the normal just whatever the plane is rotated by 90? So whatever that angle is of the plane, you rotate it by 90. You do the same thing for the other plane, then the angle between the planes should stay the same. So that's just to keep us visually in touch here. Of course, if two planes are parallel, then what can we say about their normals? They're scalar multiples, right? They're parallel also, right? That's kind of obvious. And then two planes are perpendicular if and only if you take the two normals, right, and you dot them and you get 0. So find the angle between these planes. So I give you P1, x plus y plus z equals 5. I give you the other plane. Plane 2 is 2x minus 4y plus 7z minus 10 equals 0. I want to find the angle between these two, which means I just need to find the angle between their normals, right? Well, what are the normal vectors of these two planes? Yep. Go back to the equation of a plane. Look, what was the A, the B, and the C? It was the components of the normal vector, right? And even after you multiply this all through and you get down to this, even when you're way down here, look at the A is the coefficient of x, the B is the coefficient of y, and the C is the coefficient of z. So the coefficients of x, y, and z give you the three components of your normal vector. Hey, that is a super powerful thing about equations of planes. If someone gives you an equation of a plane, you automatically know the normal vector just by looking at it. So if I look at this one up here, what is the normal vector of plane 1? It's 1, 1, 1, right? 1, 1, 1. What's the normal vector of plane 2? It would be the 2, the negative 4, and the positive 7, right? 2, 4, negative 4, sorry. Positive 7. Now, you have to, one thing you should be careful of, if the x's and y's are on opposite sides of the equation, you need to move them all to one side, right? So like if I had given you something like this, x plus y equals 3z, that's the equation of a plane, then the normal vector there would be what? 1, 1, negative 3. You'd have to bring that z over. But what if you took the x and y to the other side? Negative 1, positive 3, which is okay because that's the same vector pointing in the opposite direction. They're both normal. So just be careful with that. If your variables appear on the other side, bring them all to one side. Okay, so we have two vectors, right? N1, N2. And now we need the angle between them. So from last class, I'm not sure what note this is. Do I need to look it up? It's from 10.2. 10.3, sorry. Oh, where is it? I think it's 10.3. Yes, it's 10.3.6 is where it is in the notes, 10.3.6. We have that theta here will be equal to arc cosine of u dot v, but here I'm not using u and v, I'm using n1 dot n2 over the magnitude of n1 times the magnitude of n2. That's cosine inverse. What's n1 dot n2? n1 dot n2. 5. Right? You're doing 1 times 2, 2. 1 times negative 4. So put those together, negative 2, and then 7. Add them all up, you get 5. Now, what's the magnitude of n1? Square root of 3. What's the magnitude of n2? Is it 69? 4, 16, right? 20, and then 49, yes. And then I would just get on the calculator and do that. And I'll take a volunteer in degrees. Anyone else? Yes? All right. There we go. Questions? Still got about half an hour. This is, I said the other note was pretty big. I guess I'll keep on saying these are important, but this one is important. I mean, this one is real important. Take-home exam stuff, I ask problems that refer to this. If you have two planes and they hit each other, right? Then where they hit each other is a line. Their intersection is a line, right? Can we find the vector equation of that line? Think about what you would need. If I have two planes and they hit, right, I would need at least one point where they hit, don't I? So, because what is it we need for a vector equation of a line? Point in the direction. So I could get a point, hopefully, where they hit each other, any point where they hit each other, and then how could I get the direction? So watch this. Let's imagine that we have the normals, you know, there are the normals to those planes. You agree that that looks normal? Do I have to convince you, or are you convinced those are the normals of the planes? Okay, I'm going to slide them around. I'm going to slide them, remember, because those vectors can move. I'm going to slide them so that they're both on the blue plane, or blue line, right? So those are my normals. Check out what happens if you cross the normals. Where does that vector live? On the line. Doesn't it? That would always work. Right? Any two planes that hit each other, the line where they hit, if we take the two normals off the planes and cross them, it's got to go in the same direction as that line. Let's restate that. In order to find the equation of a line between the line of intersection of two planes, we find the point of intersection on the plane, and then we find the direction of the intersection, which is the cross product of the normal vectors of the plane, as this example requires us to do. How are you all doing with this big old long ass class that you signed up for? You know, hanging in there? It's a long time to sit. Oh, summer 2? Monday through Thursday, 8 to what though? That's still a long time. 4 days a week? Yeah. Okay. According to our calendar, our schedule, how far are we supposed to get today? All the way through 10:05? We might get a little hung up today. All right, find the vector equation of the line of intersection of these two planes. So going through the logic again, vector equation of a line, I'm trying to find R of t equals R naught plus TV. How about R naught? Any point that lives on both those planes, any point. So there are easy ways to find points on intersections of planes. You can just arbitrarily start picking values of x or y and trying to satisfy both equations at the same time. So like, for example, so I'm trying to find R naught right now, all right? I'm going to let x be equal to 0, all right? If x is 0, what does P1 give me? What does plane 1 give me? Y plus z is 5. All right, well, let's do more. Let's let y be 0 also. What would plane 1 give me if I let y be 0? Z is 5, right? Now let's take a look at plane 2. What would happen to plane 2 if I let x and y be 0? I get 7z minus 10 equals 0. But what's z? 5, right? Well, yes. We said if I let x and y be 0, right? If I let x and y be 0, then this must be true, but then that doesn't satisfy this one. So that's not a, if I let x and y be 0, I cannot have an intersection. Does that make sense? So how can we do it? We have to come up with some easy way of trying to spit out a point of intersection. We can use this same method. I picked x0, y0 just arbitrarily. Anyone have another suggestion as to what we could try? System? Well, we only have 2 equations, though. We have 3 variables, right? How do you... Oh, like set them both to 0 and then set them equal? You'll still have... Then you'll have 1 equation and 3 unknowns. You mean like the one... Look, the way I was doing it is going to get us there. It's just I restricted us too much. I said, let's let x be 0. And I was on my way. I had an equation here with 2 variables, right? And in the other one, if I would have let x be 0, I would have an equation with 2 variables, and I could have solved it, couldn't I? But then I tried to push too far, and I tried to control 2 of the variables, and it didn't work. Do y'all see that? So let me back up a little bit and not try so much at one time. Let's try letting, I guess I'll stick with x is 0. Let x be 0. If x is 0, what does P1 become? We said y plus z equals 5. What does P2 become if x is 0? Negative 4y plus 7z equals, I'm going to move that 10 over, that negative 10 to the other side. Can you solve that system of equations? Yes? You can do different methods. You want to do substitution or elimination? Elimination? Okay, if we're going to do elimination, then I'm going to write it out like this. And to eliminate, I'm going to eliminate the y variables by multiplying the top equation by 4. I don't know if this is what you mean by elimination, but this is what I mean by elimination. If you're more comfortable working with an augmented matrix, then you can do that also. What did I forget to do there? It should be 20 over here, right? I'm distributing a 4 through here, 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 and then leaving the bottom one alone. And then now that these 2 are off by a constant, I can just basically add down and get what? 11z is what? 30. And that means z is 30 over 11. Right? Once I know what z is, can I go back and get y? Can I go back and get y? Yeah, I can. I'm going to pull y right here because this is the cleanest equation I have for y. So I'm going to pull that equation down. I'm going to plug in 30 over 11 for z. So y plus 30 over 11 equals 5. Y equals 5 minus 30 over 11, which is what? 25/11ths. So let's summarize. If I let x be 0, that means y has to be 25 over 11, and that means z has to be 30 over 11. That point should live on all of them. Should live on both planes. Make sense? Now, if we all do this problem separately, are we all going to get the same point necessarily? No, right? I mean, you may choose to let y be 0 and then go solve for x and z. Or you may choose to let z be 0 and go solve for x and y. Or you'll choose x to be 1. But no matter what, if you let one of the variables be a constant, you should be able to get the other two. So that is my point. It lives on the line of intersection, right? Now, if I convert that over to a vector, I now know R naught is the vector 0, 25/11ths, 30 over 11. Okay. Now what do I need? Going back up here, I have R naught. I need V. I need the direction of my line. And the direction of the line should be the cross product of the normals of those two planes. That's right. Which are up here. So I'm going to go to a new page. V for me should be equal to the cross product of the normal of plane 1 with the normal of plane 2. The normal of plane 1, what's the normal of plane 1? 1, 1, 1. What's the normal of plane 2? 2, -4, and 7. And then I can do my cross product. This one, the numbers are a little nicer, so see what we get here. 7 take away -4, so we have 11. 7 take away 2 is 5, but make it negative. And then -4 take away 2, -6. Y'all agree? That's V. So I'm ready for my vector equation. Any questions? R of t equals the point, was it 11? Was it? (25/11ths), 30 over 11. 25/11ths, 30/11ths, plus t times 11, -5, -6. And then we can put it all together, get 11t, 25 over 11, minus 5t, 30 over 11, minus 6t. And like I said, we will all probably get different answers when we do this, but there is something that should all be the same for all of us, and that's this 11, -5, -6. We should all have that or no? Are we all going to have an 11 in front of t, a -5, and a -6? Maybe, right? Someone may decide to scale it, right? So you could scale it and it would still be okay. But if I'm grading this, one of the first things I'm looking for is, are your coefficients of t scalar multiples of my coefficients of t? Like, are they within, right? And then as far as the point, I could just check the point by plugging it into both equations and seeing if it's true, right? Questions on that? think we're probably at a point, we're almost at a point where we can stop. Almost. It's 4:15. I know that your brain has had enough probably, but I'm just going to show you this, and then we will come back and we will talk about it in depth next class. What I'm about to say, though, is probably the most important thing you're ever going to hear in this class. I'm just kidding. I'm just kidding. Go ahead. All right, so let's talk about if you have two planes in three-dimensional space, and you want to know the shortest distance between the two planes. Shortest distance. Now, these planes have to be parallel, don't they? Think about the question. If I have two planes and they're not parallel, then they're going to hit each other, right? And that means the shortest distance between them would be 0. So imagine you have two parallel planes, and you want to know the shortest distance between them. Well, if the planes are flat, like horizontal, like if I have a plane that goes like this, I have a plane directly under it like this, and here's the origin like that. And that's a pretty simple problem, isn't it? I mean, you can imagine it's just the difference of the z coordinates, isn't it? But what if we tilt the planes? So you're no longer parallel like to the xy plane. We tilt them now, and things aren't so easy. The shortest distance is still this point, right? Is that it right there? Is that still your shortest distance? No, it's not. It's actually the one that's perpendicular here, isn't it? Do y'all see the difference between that? It's not the difference of your z coordinates. So how can we find that? Well, it turns out that it's actually pretty beautiful how you can get it. So here's the construction of it, okay? Here's my plane, right? Oh, wait, hold on. Crap, did I go past? Oh, I'm sorry. I got ahead of myself. This was supposed to be the shortest distance between a point and a plane, not a plane and a plane. My apologies. If the plane is flat flat, right, and the point's above it, then it is just the difference of the z coordinates. Still, same argument, right? But if I tilt the plane, then it's not this distance, right? It's this one over here. So not so easy. So here's the very nice construction of it. So here's a plane, right? I can spin it around and move it and tilt it. But let's just imagine it's already tilted, all right? It's sitting there in space and it's tilted. And we just kind of move ourselves around so we're looking at it and we see it kind of like it's flat, all right? So we're just standing here, and then we have some point sitting in space. And I want to know the shortest distance between that point and that plane. So what I need to do is imagine projecting straight down onto that plane like a perpendicular and finding that distance, right? We want that distance. Okay, so here's how I'm going to do it. If I have a point and I have a plane, then, and that's all that's given to me, do you agree that I can always find a point on the plane? Right? If someone gives you the equation of the plane, you can just plug in some value of x and y and then figure out what x, y, and z makes the equation true. So I can always generate a point on the plane. So here we go. I just generated one. There it is. It's not directly below. It's just some random point. Then what I'm going to do is I'm going to create a vector which we'll call the b vector. That vector will connect the point I picked randomly to the point that I'm trying to get to, right? With me? Now what I'm going to do is I'm going to show our normal vector of our plane. Now the normal vector comes out of our plane, right, straight up. It could be way up here. It could be short, right? And it could be, moved around. I've just oriented that normal vector so that it's directly in line with this point. Is that all right with you? So far, though, the red one and the blue one by themselves don't give us what we're looking for, right? However, if we shift the blue vector over, because vectors can be shifted, and I line it up tail to tail with the normal vector, take out that blue one here so it doesn't confuse you, and now I project the blue one onto the red one. Remember vector projection from last class? If I project the blue one onto the red one, vector projection, then that creates a new vector, doesn't it? It's a vector that goes from here to that point. And can't we measure the length of that vector? That was called the component of one vector onto the other. And that will give me the distance. So the shortest distance between a point and a plane is the component of this blue vector onto the normal vector. The component being the measurement of the vector. Now, that can all be summarized here. It's the length, sorry. This was the component, right? This was the definition of component. And then when you actually do this computation, you come up with this, and we'll go through all that next class. Now, again, I'm just showing you constructions of this. We'll do examples when we come back. How would we find the shortest distance between a point and a line? Again, we're in three-dimensional space. So we have a line, and we have some point, let's say the projector. And I want to know the shortest distance between that point and this line. Well, again, that's because we're in three space, it's not easy to orient everything, but we can do it like this. Here's a line, here's a point. Again, I've moved myself visually so that it looks like that to me, right? Can I find a random point on that line? Yes, right? Can I find another point on that line? Can I connect a vector between them? Can I create a vector that goes from Q to P? Right? Don't I want that distance? Isn't there a relationship, trigonometric relationship between all this? Sine of theta is d over b, right? D over the magnitude of b. Opposite over hypotenuse, right? And that's how, well, you know what? Yeah, I'll look at this right here. We want to know what d is, right? I can multiply both sides by the magnitude of b. And that would give me this. Now this is the tricky part. What happens from here to here? I just introduced a 1, didn't I? The one I introduced, well, I didn't do it. Someone else did this, but I'm just showing it to you, right? What happens here is a magnitude of A over magnitude of A is introduced. The reason why it's done is because what is the top? That is, it's not up here. That's your cross. That's your magnitude of your cross product. That's that formula we had. So the distance becomes the magnitude of the cross product of A and B over the magnitude of A, and that's the formula for it. So if we go back up to this, it says, in order to find the shortest distance between a point and a line, all you have to do is take any vector on the line, call it A. What's a good vector to pick that's always on a line? If you know the line, do you know a vector on it? Which one? There is one, the direction vector, right? You always know the direction vector of the line, right? If someone gives you the equation. So I just pick some vector, direction vector, and then I can create the vector that goes from here to here. I cross these two. I take their magnitude. I divide it by the magnitude of this one, A, and that's the shortest distance. We'll do more of that next class. Has the sign-in sheet gone to everyone? Do you want me to stop? Because feel like I can keep talking, so y'all might want to just pack up and go. I'll send your homework email, okay, today.